Okay, on Friday we started our chemistry on reversible reactions. And obviously a reversible reaction, if we remember, is where the reactants turn into product, but then the product actually reacts back and returns to the reactants again. And this is what we call reversible. She's insisting, isn't she? Reversible. R-E-A-C-T-I-O-N-S. Okay. Reversible reactions. Now, when we're looking at chemical equations, so for example A plus B, if it's going to turn into something, we use a single arrow. In a reversible reaction, we use double arrows. Let me show you. So the single one would just be where something doesn't reverse, but then if you wanted to do a reversible sign, you do an arrow that way and an arrow this way. So if you have a single arrow in a chemical equation, it will tell you DHA, DHA, that THE, Brilliant, keep going. There you are. Finish the sentence. R-E-V-E, lovely. R-S-I-B-L-E, fabulous. Yeah. That the reaction is not reversible. If it is a reversible reaction, then it is signified by what symbol? By the symbol of an A, R, R, O, W, an arrow, G, O. Keep going, there's your eye. Arrow, G, O, I, N. With an arrow going B, O. You can be more careful with the pointing, I know you can do it. T, T, H, W, A, Y, S. Yeah, fab. Now that's arrow going both sides, going both ways, is called an equilibrium. E-Q-I-L-I-B-R-O-U-M. And that basically stands for the status quo. So the double arrow sign means the status quo also is called the E-Q-U-I-L-I-B-R-O-I-U-M-S-I-G-N. Go for your N. Brilliant. Yeah, the equilibrium sign, another word that I struggled to say. It's quite a new word I find hard. Okay, so that will become more important a bit later on. So what about within a reversible reaction? What actually happens? Well, if you imagine to start with, you only have A and B. Okay, so you only have reactants, sorry, A and B. Okay, so that's A and that's B. It will then equal, as we know, double equilibrium sign. So when it starts to react, those products start to turn into C. That's stage 1. Okay? So it starts to turn into C. Stage 2 is where you have a little bit of product C available. So those products then start to turn back into A and B. That's stage 2. Then slowly it starts to increase because there's more C and D. The C and A and B go over and C and D go back and so it keeps going. And stage 4, so in stage 3, sorry, to make that a bit clearer, in stage 3, A and B still react a bit quicker than the product C going back to A and B, but there's still a lot of movement going on. And stage 4 is actually a state of equilibrium, which is where there's exactly the same amount of reaction going on from A to B, then back to A, going back again. So you can see that it starts to move around. So within the reversible reaction, there are how many stages? F, O, U, R, S, T, A, G, E, S. Yeah, there are 4 stages. And in the first stage, is there any reversible reaction going on at that moment? No, and that's because at the moment we haven't actually made any product E, Y, E, T. Okay, so then in stage 2 and 3, A and B start to react and go over to become product C. But what happens with product C? It starts to decay. R, E, T, U, R, N. Starts to return. T, O, 2, R, E, A, R, E, A, C, T, A, N, T, S. Yeah, it starts to return to the reactants. So you start to get more of a flow. Now by the final stage, stage 4, what do we know about the rate of reversible reaction between A and B and C? That the rate of reaction is T, H, E, S, A, M, E. That's right, so we'd say at this point we'd reach the point of E, Q, U, I, L. Yeah, fast. Keep going, keep going. Over your I, keep the word going. I, B, I, R, sorry. I, U, M. Yeah, fab. So because you have the same amount of product is being made, the flow's the same. So we're back in a state of equilibrium. Okay, so let's look at an example with actual chemicals. The example we're going to look at is called iodine monochloride, which is a brown liquid, and chlorine gas, which is a green gas. Now these react to produce yellow crystals called iodine trichloride. Okay, so the iodine monochloride is a yellow liquid, the chlorine gas is a green gas, and they will react together to produce let's go. Okay, take your time. know the answer, it's just practice. Go for your O. O, D, I, N, E, T, R, I, C, H, L, O, R, I, D, E. Yeah, iodine trichloride. Now as we start to go through from the stages 1 to 3, iodine trichloride actually then starts to react. Once the chlorine gas has built up in concentration, the iodine trichloride returns back to iodine monochloride and chlorine gas. So the key point here is that as soon as the chlorine gas builds up in its level of C O N D E N T R A T I O N. Yeah, as soon as it builds up in concentration, the iodine trichloride will then turn back into iodine monochloride and the gas C H L O R I N E. Yeah, into chlorine. Okay. Is there anything we can do to prevent this from happening? What do you think? If you were trying to prevent the reaction from becoming reversible again, what would be the logical thing for you to do? I N C R E. Great, come on, really good. A C E, increase. I O D I N E. Keep it going, it's fabulous, honestly. This is like a higher end question. M O. Keep it going. Go, come on, keep it going. D. Go for your D. It's me getting mixed up then. Go for your D. Sorry, darling, I've got one letter for myself. Increase the just finish off with your D and your E. You're absolutely right. Absolutely right. Oh, yeah. Absolutely right. Come on, finish this up. You can do it. Let's finish this sentence. Finish this sentence. Go for your D. You've only got D you need to do. D, E. Yeah, increase the monochloride. Yeah, exactly. And the effect of increasing, making sure you increase the amount of iodine monochloride will mean that the chlorine gas D, O, E, S, N, O, T, G, E, T, 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 O, C, O, N, C, E, N. Go for your T, come on, go for your T. Keep it going, T, R, great. Keep it going, come on. T, E, D. So it definitely will not get to does not get too concentrated. And the reason that we don't want the chlorine gas to get too concentrated is because THE start Come on, this is fabulous stuff, fabulous stuff. Come on. It's great. Drop that down then. Exactly that. Okay, so by managing the relative properties of reactants and products, we can change how much product we actually get. By changing the reaction, we can change how much of the product we actually get. So in reality, what we're doing is we are changing the keep going through A, C, T, A, N, T, S. Yeah, we're changing the relative, which is what you already knew what to do anyway when I asked you earlier. That is what you have. Okay, now there's one something we know that we're part of that actually uses reversible reactions all the time itself. Can you think what might use reversible reactions a lot? You. Yes, yeah, us. Yeah, our bodies. I mean, that's quite a complicated thing to start judging how much you need to stop a reaction from reversing. I'm sure there's people got lots of jobs to do that in laboratories around the world. But our body does it all the time, constantly. And many of the things that control them in our bodies are the special chemicals called enzymes. So the important things that manage the reversible reactions in our bodies are the special chemicals called E, N, Z, Y, M, E, S. Yes, enzymes. And there's one particular area that we talk a lot about enzymes within our body. And what's that area that we talk a lot about? Digestion, exactly. And if the enzymes in there aren't adjusting the relative proportions of the reactants correctly, then that must be one of the reasons we get problems around that area. So it's a really important process that's around not only do we use in chemicals but also in ourselves. So just lastly, what did you think about reversible reactions today? And I thought it was A. It was A. You have to move your arms, I'm not sure where you're going. Think about where you want to go. I thought it was interesting, and it was a W A W A. Did you want W A? Yes or no? Yes. Okay. Carry on then. Oh no. Okay. So I thought it was interesting, and it was a. Let's go from there. And it was a. Oh, shit. I N T E R E S T I N G S E S E S E. Okay. S S I O N. Oh, full stop or more? Oh, okay, fab. Because today I noticed you didn't try to leave the table today. Was there any reason for that today? Sometimes I know you have to leave. Was there any reason why you didn't today? I W A S E E E. Keep coming on. Doing fab. E N J O Y I N G I T. Okay. So sometimes do you leave the room because you're not enjoying it? S O M E T I M E S I C A N G. No? Is that right?
More.
Sometimes I can. G E T B O R E D. Okay, that was That's interesting. I think we all feel like that about stuff. Sometimes I can. And how about when you do feel bored, would you say it could be the subject or the way the session's being presented, or both? Both, okay. And what happened today that maybe made it more interesting that you didn't have to leave? What could you tell me that might help me to make the sessions more interesting for you? This is fab. I love talking to you about stuff like this. J, keep going, come on. E, C, T. It's an interesting subject. Okay. Well, you know what? There are going to be subjects that interest you more than others, because that's what it's saying for everybody. Sometimes, even if it's boring, we have to do it. Yeah? So we have to do that. So when something's not interesting you, maybe you could tell us and we can help you. What do you think about that idea? Tell us during the session rather than leaving the room all the time. I-T-H-I-N. Okay, I think. Come on, finish this off. Come on. I think I would T-E-L-L-Y-O-U. Yeah, you think you could tell me? And then we could work together and work through that, couldn't we? So maybe in future you can tell us, and then we can either adjust the session, we can maybe work a bit faster, or we can add more relative things. I want to say more relative things in. But the other thing I want to say is, sometimes you do leave the room, you told us, just when you're hungry. So when you come back, I'll just finish off that with you.